always on Mondays, the graduate seminar series, and from 3 to 4, and always in the same room. And here, if you go to my Twitter account, and then you click in this figure, you will see, how can I make this bigger? Okay, it's not working. Okay, wait a minute. All right, so there we go. This was Robert today from Pioneer Resources. Next week there is a seminar from Alex Epstein about energy policy. I strongly encourage that you come to the seminar and attend from Robert Zimmerman. I don't know if you know the book Jagger, Cook, and Zimmerman about rock mechanics. Well, it's this Zimmerman, and he is a world expert in rock mechanics, and he's going to deliver the seminar 2 weeks from now. Then we have Kitty Milliken from BUG on petrography, and Sam Crevor about multi-phase fluid flow, and we go more into a direction more fluid flow, acidizing. So for geomechanics, probably the last seminar strongly related to geomechanics is going to be the one from Professor Zimmerman from Imperial College. I strongly encourage that you attend. Okay, so a few things. Monday from 3 to 4 in the same room. So right before this class on Monday, we have the seminar. Okay, let me talk about a few things in order to get organized. Remember that we do not have a final exam in this class. Instead, we have a final project, okay? For that final project, you are required to do 2 things. First, you need to prepare an abstract, and let me get over here. So in green means that we have already gone through that. You have to prepare an abstract about your final project. So at the end of the semester, you're going to have to make a presentation about this final project, but I don't want you to do that 3 days before the presentation. You should start thinking about that, and you should choose a project about what to work on. And I have a few more details about this. The deadline is going to be November the 13th. And let's go over here. No, not there. If you go to Files, and then you go to Final Project, here you will find the guidelines about this project. Again, deadline is November 13th. And for now, for this day, I just asked you the abstract, and then later, at the end of the semester, you're going to have to do a presentation, which is going to be about 10 slides. It's not very long, okay? All right. I have some guidelines about how to write an abstract, and I like that you write this abstract as if it were a paper, a conference of a journal paper. And you know, there are some basic questions that you have to answer in the abstract, like, you know, just a broad introduction about the problem. For example, if we were to write an abstract about Dr. Hertz's presentation, you know, we'll say something like, hydraulic fracturing has become very important for petroleum engineering in the last 3 decades, something like that. Then something about more detailed. We will say there, however, nobody knows the complexity, the actual complexity of fractures in the field. And probably that will be also close to the specific problem about the complexity. And then you say, for example, for this presentation, one aspect that hasn't been studied is the influence of mixed mode fracture propagation or fracture complexity. And then you say what you do. Well, we do this, we do that, and what are your conclusions? Well, for this project, I know that many of you are working on some research project right now with your advisors, but some of you may not. So I have several options for what the project can be. And these are the three options. First one, you could write an abstract and make a presentation about an original research project that you're working on right now. And I think that would be the ideal case, because in that case, you're working for your research project, but you also utilize this class to work on that a little bit, on that too. And of course, you know, ideally that should be related to geomechanics. If it's not related to geomechanics, probably you have to do something else. And that something else could be that probably there is a topic that you like and you never got to study in depth, or probably there is something that you like and that you would like to work on that right now. And probably, you know, could be a review about hydraulic fracture test in the laboratory. And then you just go through the papers, you do literature review, and you prepare a project based on that. And if you don't want to do that, or if you want another choice, that could be a case study. And in that case study, you may be interested, for example, in a literature review and a case study about induced seismicity in Oklahoma, something like that. So you say the causes, you say what's going on, what are the geomechanical fundamental aspects of the problem, and just write a project based on that. So it's up to you, but if you need some help about choosing a project, just let me know. Stop by my office and we can discuss that. And I can help you. If you don't have any specific project to work on, I could suggest a few projects. And based also, ideally on matching your expertise or the direction in which you want to go with something that I might suggest. And once you finish your abstract, just upload it. And I'm going to, again, make the assignment. You upload it as a PDF, as usual, with the homework. And then I'll give you feedback about that. And I'll let you know if you need to redirect your project a little bit or not. But I strongly encourage that we talk about that before, and we agree on that project. Okay? Any question about that?
So abstract due is November 13th.
Yes. So like more or less 20 days from now.
So and the final project due is.
It's well, that's something that we have to talk about, because I didn't say that yet, because I wanted to agree with you. Let's see. Final exam. Okay. No, that's the second exam. That's the second exam, which is going to be the second part, whatever we start seeing today till the end of the semester. But the final project is going to be at the time of the final exam. And you can check that in the registrar, so we can check it right now. Okay. Let's see who is faster. So current finals. Our class is Monday, Wednesday, and Friday. All right, Wednesday, December 18th. Sorry.
This is saying Monday.
Friday, December the 13th. Okay, that's not too bad. But if we had to do like December 18th or something like that, probably some of you would say, no, you don't want that, right? I don't want that either. So probably this day is okay. And well, 7 p.m. to 10 p.m. Friday. Do you guys want to
Should we
want
have a
come
chemist
hang out with me at the Friday 7 p.m.? Probably not very likely, right? Not me, yeah. You want to be somewhere else? Me too. Believe me. So we'll find a common time, and then we'll have these presentations. Okay? And it will depend on also your final exams and my availability, but we'll find a time around this time so we do that presentation. Okay? Okay. Then I think we're good with this. Remember, we don't have a final exam, but we have a final project, and you need two things in order to get a grade for that: the abstract, which is going to be part of the grade, and then the final presentation, which is going to be graded based on my feedback, but also on the feedback of all of you. Jack?
Besides the PowerPoint presentation, do we need to give you anything else, like our work?
No, that's it. PowerPoint presentation. But notice that the grade is not going to be based on like the PowerPoint presentation. It's going to be based on my appreciation or what what I think is the quality of the contents of your presentation, but also based on everybody's perception. So I don't remember the weights, but I think I'm going to put myself as probably 30% of the grade, and 60% is going to be the rest of you by peer evaluation. All right? Okay. So, well, let's continue now with the regular lectures. We have seen one important aspect about geomechanics, which is pore elasticity and what is the influence of pore pressure in deforming rocks. But there are some other phenomena that can affect deformation. It's not only about pore pressure, but equally important is also temperature. And in order to solve problems of geomechanics, including variations of temperature, we need to understand thermoelasticity. And this is going to have several applications. Probably one of the most important ones, and where there is a lot of effort now being done, is on geothermal energy. The Department of Energy started investing in hydraulic fracturing more or less in the 80s, trying to look to produce hydrocarbons from tight reservoirs. And it took a significant time for that to take off, but now it's very important. And the Department of Energy now is also spending significant resources into understanding better geothermal energy. And for geothermal energy, some of the rocks are very tight too, so they also require hydraulic fracturing. And in geothermal energy, when you do hydraulic fracturing and you do injection of fluids, it's very important to get to know what is going to be the variation of stress due to variation of temperature of the host rock. So there are two types of geothermal energy. There is shallow and there is deep. The one that we are interested in mostly in petroleum engineering, or I should say in terms of producing significant amounts of energy, not just for a few houses, but for an entire city, is deep geothermal energy. And the applications of thermoelasticity are for understanding hydraulic fracturing and also for understanding what is the variation of stress with temperature and which fractures have a large ratio of shear to effective normal stress. Because the higher this component, the higher is going to be permeability in brittle rocks. Geothermal energy is also important for, thermoelasticity is important for drilling applications. When you drill a wellbore, you're using mud, which is usually on the surface, and it depends where you are, what the temperature of the mud is going to be. Depending on how deep the wellbore is how much the mud is going to take temperature as it goes down. But in many applications, that mud is going to have a lower temperature than the formation itself. And when that happens, you're going to be cooling off the wellbore, and when you cool the wellbore, you can produce an increase of the tensile stresses around the wellbore. And we'll get back to this. But basically, your hoop stress, because the rock is shrinking, is going to decrease. There are some examples in which you are drilling a wellbore, the wellbore is perfectly stable, and with a given wellbore mud at a given temperature, but then you go and do a pass of a logging tool, and some logging tools require temperature to be certain a given value, because otherwise some sensors will not work very well. So when you change the wellbore mud, and if you put a mud which is cooler, you may trigger tensor fractures, and your wellbore may not be stable anymore. And that's just because of the effect of temperature. This is going to be also very important for fluid injection. In applications like EOR or in other pure injection cases, usually you're also injecting fluids that are on surface into a formation that may have a higher temperature. If you inject the fluid again into a formation with a lower temperature, you should expect the stresses to change because of the change of temperature. And for example, this happens with water, but for example, I worked with a student on injection of carbon dioxide for EOR and also for just disposal, in which depending on the temperature of your injectant, you may have more or less variation of stresses in situ that could help some hydraulic fractures to propagate. And we're going to see an example about that later on as we get to the end of thermoelasticity. But again, here you could also have water, or here you have chemicals. The issue is always, what would happen with the contrast in temperature between what you inject and the reservoir temperature. Can anyone give me an example in which your injectant has a higher temperature than the formation? Well, but I mean for engineering purposes. Oh, okay. Yeah, that would be a natural case.
Is AGD, like in Canada?
Very well. What do you inject?
High temperature, water.
Water, and sometimes also you inject steam.
Yeah.
Okay, and so you inject water in vapor phase, and the temperature can be very high, 200 C, 300 C, and sometimes a lot higher than the reservoir temperature, and that is going to cause the opposite. It's going to cause the rock and the fluids inside to dilate. Sometimes the dilation of those fluids, if it's under undrained conditions in which the pore pressure cannot dissipate, is going to increase the pore pressure, and that pore pressure is going to lower the effective stress. That lower effective stress is going to trigger shear fractures.
Can you repeat that one more time?
So when you inject a very hot fluid like steam, you're going to heat up everything in the rock, the solids and the fluids. But likely the fluids, especially if they have undergo a very large temperature change, may go into the vapor phase, the original fluids. And as they do, they occupy more volume. They occupy more volume, but you dissipate that increase of pore pressure in terms of, because you need more space in order to have more volume. But if you don't have that space, pressure is going to increase. Pore pressure is going to increase. And if pore pressure increases, your effective stresses are going to go down, assuming that your total stresses are not changing. And if that happens, then you're going to produce shear fractures in the reservoir. And that's an important mechanism, for example, in some of these oil sands that help recovery, is the formation of shear fractures, allowing the fluids to go more easily through the rock. And
so if you inject a colder fluid, that would induce more compaction?
contraction.
Contraction.
Yeah, contraction. Yes. And here is the example. Now, last, we could also use changes of temperature in hydraulic fracturing. All right. And I have a question now for you. Would you inject a hot fluid? Let's just restrict this to unconventionals. And with the conventionals, I mean tight formations, like a shale. Would you inject a hot fluid or a cold fluid in order to have more, let's say, fracture propagation? Cold?
Fracture propagation?
Fracture propagation. You know, as we saw in the seminar before, many times you want to increase the complexity of your fracture to have more surface area and to help the fluids to go into the wellbore more easily. So would you inject a cold fluid or a hot fluid? Okay, let's go with the cold one. Why?
Because tensile failure, and you can get profit in something that's opening like that.
The colder the fluid, the more contraction you will induce in the formation, and that sometimes can cause additional tensile fractures in addition to the ones that you're causing with the fluid. There is actually a project that some people have proposed to do cryogenic fracturing. Basically, what you do in this case is you inject liquid nitrogen as a fracturing fluid at very low temperatures so that you can lower the temperature of the formation, and that can help fractures to propagate. The problem with that is that there is a finite heat capacity of that fluid to cool the rock. So it does help, but the question is, how much? And although by propagating a fracture with by pressure, you have almost, let's say, an infinite source of power on surface on your pumps. When you inject a fluid, a cold fluid, all the budget of energy that you have in temperature is the heat capacity of your fluid. That's it. So some people have tried and argue that this can help hydraulic fracturing. It does help. The question is, how much, and again, if it is economical or not. But it does help hydraulic fracturing.
Can you explain that cold fluid is more contraction and
We'll go into equations right after this introduction, and we'll see how that happens. But for now, let's just keep it as the high-level introduction. And let's go with the opposite. What about if you were to heat up the reservoir?
We just mentioned that earlier.
And so what is going to be the consequence? But now this is going to be an unconventional, right? And in this case, there are some people that have proposed to microwave the formation So you heat it up with a radiation, and the objective is that if you have a rock with water in the pores, as you heat it up with a microwave, you're going to increase the temperature of the fluid molecules. Those fluid molecules may go into, I don't have blue color. They may go from the liquid phase into a vapor phase, and as they do, again, they will try to expand. If the permeability of the rock is low, the fluid cannot go anywhere, and if the fluid cannot go anywhere, that means that your pressure is going to increase. And this is again undrained loading, because the fluid is not going anywhere. It's just changing phase, and as it changes phase, its pressure is increasing. And when it does that, the argument here is that you could create some fractures out of these pores and create microfracturing that is going to increase the matrix permeability of the rock. And I'm not sure, there have been some field trials of this, but people from Aramco Services were pushing this idea. Again, one of the problems is how to get all that energy further away from the formation. Probably with this method, you can heat up very well the near wellbore region, but getting further away, it's very difficult. Similar to this, it's a process of undrained loading with source rocks. When organic matter transforms into oil and gas, usually also you require more volume for the same mass, and also that can crack some pores in unconventionals when they are forming, and which is similar to this, but in this case will be caused by radiation and increases of temperature. You had a question, Bethany?
I was just wondering, I guess after someone would do something like this where they create the microfractures,
Yeah.
would that then be fractured later on to connect them to a wider network? Because otherwise I feel like they would just...
That would be the idea.
Okay.
Probably what I would do is to heat up first, to increase the pressure everywhere, and then fracture it.
Okay.
But I don't know exactly what these guys were doing.
How would microwaves affect your oil or your gas? I'm not sure. Like, could you crack it?
Well,
Or, like,
that's a project. There's many people interested about, like, helping oil and gas to get produced by immature oil and shales, that they are not quite in the range of producing oil and gas, by helping them to generate oil and gas. So you could do that, and I know that some companies are interested on that. But again, it's, is that economical? It can be done, but is it economical or not? That's another question. So you could do this experiment. Let me see if we find something in YouTube, because this can be easily done if you put a rock in a microwave and you heat it up. All right, so first of all, don't do this at home, Stephanie. Okay, you might break your microwave. Let's check. Let's check these two. Okay. Okay. Fast forward. Okay. Let's see what happens.
Can you make it larger?
Oh, yes, sorry.
It's in water.
Ah. No, I don't see anything happening here. Okay, I think I have to do this myself at some point.
Oh no.
No. All right. So
There was another one.
yeah, but I think it's the same.
Oh, it's the same one. Yeah.
Turn rock into the crease. Okay. Okay, let's check this one. Okay, don't care about this. All right, let's check this guy. What is that?
Welcome to a scene on social media where normal people
appears to be a good candidate for something called the Geo. Geo is formed of volcanic rock and ash in bubbles or spaces. Over time, minerals will crystallize in and fill up the area beneath.
Okay.
Here.
Well, there's a key variable here that is going to tell you if the rock fractures or not. I don't see any change. I think he cracked it open. Well, I don't know if this geo will have significant water. I don't think so, right, inside? Okay, well, I'll try to make my own video then. No, that should be fine. Probably we can do that in the laboratory. But the main difference here is that either if you microwave a rock with high permeability like a sandstone, probably nothing was going to happen to it because the water is just going to get out of the pores very quickly. And that will be a drain loading. And if your rock has a very low permeability and the water doesn't have enough time to escape, it's going to fracture the rock. So you can microwave two rocks at the same time. One with high permeability probably will not fracture, the other one with low permeability, it will fracture. I'll test that. I'll let you know how that goes.
Would you have to put them in water, or could you soak them in water and then put them in the microwave?
Yes, you have to saturate it with water before. So I don't know in this case what they did, but if the rock doesn't have any water inside, then nothing is going to happen either. So you will have to saturate it first. And saturate it very well, so when the vapor expands, it's not that it's just taking place of the gas, but it really has to expand. Yeah. Okay. So the underlying concepts in all of these processes is that if we have a positive change of temperature, we're going to call that a dilation. And in this case, the volumetric strain, or as we were calling it also in pore elasticity, this epsilon is going to be less than 0. It's going to be a negative value, and we're going to call this dilation.
I thought dilation has something to do with shear.
No, it's in general dilation. Like, for example, we're going to see that in thermoelasticity we need a coefficient of a linear dilation coefficient, tells you how much the rock expands with a change of temperature. If we have a decrease of temperature, usually we'll see that rocks will tend to shrink. And in this case, the volumetric strain is going to be higher than 0, and then we'll call this a contraction. And we're going to go under the assumption that either if you have a change of temperature which is positive or negative, we have no shear strains. And this kind of makes sense, but it makes sense only in an isotropic material. And a lot of our theory is limited to isotropic materials. We're not going through the anisotropic materials. We did a little bit for elasticity, but remember that real rocks are not isotropic, are not homogeneous, and therefore some of the things that we are taking as theory, they are a simplification. And just as an example, let's see what the importance of isotropy and also homogeneity is. Okay, let's say that we have a rock which is layered, and the layers have a different coefficient of thermal dilation, which means that, let's say you increase 10 degrees C, and one rock is going to expand more than the other. What is going to be the effect of that? Do you think you can create shear stresses? Why, Stephanie?
You say Bethany or Stephanie?
Stephanie, I said Stephanie.
Why would you get shear stresses?
Yeah.
Because one contracts or dilates more than the other.
And where would you get those shear stresses?
At the layer boundary.
At the layer boundaries, right?
Yeah.
So this will look something like this. One expands, but another one expands more than the other. And in order to be compatible in terms of deformation, you're going to generate stress that, let me think, this material at the interface, you're generating stress like this at the interface. In this case, we're assuming that the rock is not breaking, you're generating stresses, but if the shear stress is enough, higher than the bonding shear stress, then that's going to break. So in this case, you are creating shear stresses with changes of temperature. But if your material is isotropic and is homogeneous, you will not have that.
What you are showing over there is stress and not strain.
Stress.
It's stress.
And strain at the same time, because I'm showing the deformed configuration of this. So probably, if you want, probably we could do this. It could be smoother, meaning that it didn't break yet.
Dilation coefficient? Is that
Dilation coefficient, yes. Beta is dilation coefficient. That's what we're going to see right now. All right, so we need to put this into equations, okay? Because we want to solve these problems, and ideally we want to put them in a simulator or into some sort of model that allows us to quantify what these changes of temperature are going to produce in terms of stresses. And in order to do that, what we need to do is we need to modify the constitutive equation in order to add the thermal part. What is the constitutive equation for linear elasticity? You should know this very well. The C matrix times strain. All right, so what we're going to do is that constitutive equation which tells us the stresses as a function of strains and properties of the material, now we're going to add a component that tells us what is the influence on stresses of changes of temperature. And let me explain what's going on in here. This is the identity matrix, or the identity matrix in this case. This is change of temperature with respect to the original condition. And this one is the thermal dilation. And one more thing is the linear thermal dilation coefficient. And I forgot one thing. Let me add it, let me move it a little bit. 3 beta, and here K is the bulk modulus. All right, so you can either show this equation from doing the examples that we're going to do now, or we're going to do the opposite. I propose equations, and we verify that it makes sense.
For the changing pressure, what units? Kelvin?
It depends how you define your beta.
Okay.
So notice that here we have stresses, units of pressure. We have K, unit of pressure. So if this is, let's say, centigrade, this must be 1 over centigrade. This is Fahrenheit, this must be 1 over Fahrenheit. Okay? All right, so let's see some examples that are going to help us understand what do we have now in this new constitutive equation. And let me just clarify also that we don't have pore pressure in here. And you can use this equation whenever the pore pressures are very small, or whenever you don't have any porosity and fluid in the pores. But we just go with the thermoelastic part. We'll add porosity later on. All right.
And this is assuming isotropic.
Yes, because we're assuming that in the 3 directions, the thermal dilation coefficient is the same. So this is an isotropic material. You could have materials with anisotropy, and this beta, instead of being just one number scalar, it will be a tensor. All right, so let's go with an example of dilation. And this example of dilation, we're going to say this is free dilation, or also we could call it unconstrained dilation. And basically, we don't have any stresses. We're just heating up a rock by increasing temperature. So if we don't have any stress at all, then in this equation, the stress is going to be 0. And therefore, this is going to be 0. And from here, the only thing I have to do is to calculate the strain tensor is going to be the, if I want to move this on the other side, and I multiply the inverse of the C matrix to the left, and then I just get strain, and the inverse of the C matrix is just going to be the compliance matrix times this. And let's write now this not in terms of matrices, but as a vector. And what I'm going to get is that, notice that, I need to clarify one thing before I move on. Notice that we have an identity matrix, all right? this means two things. That is isotropic, so the beta goes the same in all directions, and also means no shear components. So the stresses are not going to be affected by the shear stresses are not going to be affected by changes of temperature because I have an identity matrix here. And the stresses are going to be affected all the same in all three directions because this is an identity matrix and basically 1, 1, 1 in the diagonal and zeros everywhere else. So the identity matrix then is telling us that we have an isotropic material and we have no shear components. And because of that, now I can just pay attention to the elements in the diagonal, and these are going to be equal to compliance matrix, which is this one, of an isotropic material 2 times the number that comes right from here. I could write the identity matrix, or I could also now, since I wrote it as a vector over here, this one is also going to be a vector, and this is going to be 3 beta k delta t and each of these strains, they're going to be all the same, but let's just solve for one. It's going to be 1 minus 2 times Poisson ratio divided Young modulus times 3 beta k delta t. And from here, let me get the negative sign over here. Anyone recognizes what the term in between the dash line is without the negative sign? The bulk modulus, right? Yeah. So this is actually K. Let me write it over here. So K divided by K is 1, and this is just beta delta t. So each of those strains is just the coefficient of linear expansion times the change of temperature. Again, I don't remember if I wrote this one. Yeah, I wrote that before, the linear thermal dilation coefficient, right? So if I have a positive change of temperature, positive times positive, and here I have a negative sign, that's going to give us a negative change of strain, which means a dilation. If I have a contraction, if I have a reduction of temperature, I would have, wait, let me say again. I have a positive change of temperature, then I'm going to have a dilation. I have a negative change of temperature, I'm going to have a contraction. Or let me write in terms of, let me be consistent with this. Positive change of temperature, contraction. Negative change of temperature, I get confused with the words. But the first one is dilation, negative. Second one is contraction, positive. because remember, we're assuming that contraction is positive, compression is positive. We are working with a geomechanical convention, not with a pore elasticity convention. Okay. Well, now that we know this, it would be interesting to get to know some more or less real values of this coefficient. And this coefficient is defined in a way that it should be a positive number because it's a property. And it's usually in the range of 10 to the minus 6 to 10 to the minus 5, 1 over Kelvin. And this is the same as 1 over centigrade. But it's not the same as 1 over Fahrenheit, okay? But in K or in centigrade, it's going to be the same. And in some applications, you can have very large changes of temperature, as large as 100 degree Kelvin. So let's assume 100 degree Kelvin and these coefficients of thermal dilation. What is going to be the strain caused by such change of temperature? So that's going to be 100 times that, 10 to the minus 4 to 10 to the minus 3. And those are relatively large deformations. I don't know if you remember when we were making these models about tectonic strains. Tectonic strain was a few thousands, was very small in order to produce a large stress. When you run experiments in the laboratory, also strains are relatively small in order to produce large stresses. And of course, it depends also on the stiffness of your rock. And the stiffer the rock, the smaller the strains you need to produce a large stress. Let me see if I find an example here. Probably here. I want a real example. No. Let me see the next one. I remember I had one. Okay, here. So here you have an example of shale. And you see that the strains are in the order of thousands to produce stresses in the order of several thousand psi. And for this type of rock, if you have stress in the order of 1,000 and strain in the order of 1,000, then the Young modulus or the stiffness modulus is close to 1,000,000 psi. 1,000 divided 1 over 1,000 gives you 1 million. And what we just saw is that for strains in the order of thousands caused by a very large change in temperature, we could have stresses in the order of 1,000 psi or so, which are relatively large. And that's what we're going to do now. So changes of temperature then in typical rocks is going to depend just on the dilation coefficient, and they could be as large as a few thousands. Strain. The strain is unitless, and it's going to be in the order. Let me write it this because it's very difficult to say for me. It's going to be thousands, right? 1 over 1,000. All right. This was a case, an example of dilation. And notice that dilation is independent of the Young modulus. It just depends on the linear dilation coefficient of the material. All right, and for typical rocks, it is this number. Well, let's see the other side of the same phenomenon, which is constrained dilation. And in constrained dilation, we increase the temperature, but as we increase the temperature, we do not let the rock expand. I remember now this was one of the issues with, at least from my point of view, from heating up a reservoir with high temperature, which is that you can blow up a rock in a microwave on surface without any stresses, but it's not going to be the same in the subsurface because it's going to be subjected to stresses and to a confined condition in which the rock may try to dilate, but instead of dilating, if the expansion is constrained, it's just going to build up stresses. And it's not going to blow up. It's just going to have increases stresses if you do not let it to dilate. So we increase the temperature here, and we heat it up, and let's see what happens with the equation. Same equation that we used before. Which term is going to be 0 now? If we mean constrained dilation, that means no strains. So this one is going to be 0. And we get straightforward out of this equation that, remember, shear stresses are going to be 0 because we have an identity matrix here. So I'm going to simplify this to the vector form of this stress tensor. And this is just going to be 3 beta k delta t times identity matrix. That's it. And let me add the sign. In all directions, then we're going to have an increase of stress, which is going to be just 3 beta k, where k is the bulk modulus delta t. And now we do have the bulk modulus. For a particular stress on one direction, then this is going to be the result. And let's say for a typical bulk modulus of a rock, this is more or less a stiff rock, but there are stiffer rocks, of 10 gigapascals. And let's say a delta T of 100 degrees C or 100 degree K, which is the same thing. Let's do it in K, since we were using K before. What is going to be the induced stress? And let's remember that we said that let's use a high beta, just to make this a little bit more dramatic, of 10 to the minus 5, 1 over k. So sigma 1, then it's going to be 3 beta 10 to the minus 5, 1 over k. And the k is 10 gigapascals, which is 10 to the 9 pascals times 100 C. Let me, I don't like to break equations, so let me write this again. But you should try to fit all of that in one line. All right, so 3, 10 to the minus 5, 1 over k, 10 to the 10 pascals, and 100k. So k with the k goes. And what is sigma 1, 1? Minus 5 plus 10 is going to be 5. So that's going to be 3 to 10 to the 5, right? And that's going to be equal
30
Okay, let me see if this is correct. So 10 gigapascal is that 10 to the 5 pascals, right?
What about 10 to 100?
Oh, the 100, the 100.
It's
So
seven.
that's why my number was 10 to the 5. I don't think that's the question. That's the answer. So it's 10 to the 7, and which is equal to 30 MPa, and which is equal to more or less, if I remember correctly, you can do this 30. Well, it's easy actually. 30 times 145, and that will be equal to more or less 4,400 psi. So that looks like a huge stress to me. So we're generating thousands of psi's by increasing the temperature and not letting the rock to expand. And also from the signs, remember, if we heat it up, positive change of temperature, and not let it expand freely, this is going to be a compression. If you lower the temperature, this is going to be a tension. What is a typical tensile strength of a rock? About how much? But I mean, let's say a very tough rock. What is its tensile strength? 5 what? 5 megapascals. Does everyone agree with Stephanie? Okay, let's look up over here. I mean, I remember the numbers, but I just want to show that so you believe me. Tensile failure. Tensile failure, typical rocks, or typical tensile failure, tensile strength of rocks, in the order of 5 megapascals. And there are some rocks which are very strong, and you can get, especially when you go into metamorphic and igneous rocks, over 10 megapascals, but usually not a lot higher. And there are some other rocks that have no tensile strength at all, and some others that have a limited tensile strength. But those Berea sandstone that we were testing here, those have a few megapascals of tensile strength. So to me, this stress looks like with a very large change of temperature, it's going to be enough to produce tensile failure. And actually, in some of the examples I was telling you about that I was doing some research on of injection of carbon dioxide, you do get to changes of 100 C. For example, if you were to inject a fluid which is on surface near Arctic regions with temperatures in below 0 into a very hot formation with a temperature in the order of 100 or more, there you have a change of 100 degrees C. More often it's going to be less, right? But it's not unreasonable to think change of 100 degrees C. Okay, Jack?
Yes, so in the equation, you said it's a constraint dilation, but is it a constraint problem or it's unconstrained for the fluid?
Well, no, we are not taking into account the fluids here. But that's a good question. In drain conditions, if you're taking into account the fluid, the same thing will hold, because the solids are also dilating. So what is creating the dilation in this case, or what is causing the compression of the solid framework, is the dilation of the solid part.
Okay.
If you had a fluid, then your effective stress may change with time. It may go into something which is low effective stress to high effective stress as the pore pressure dissipates with time.
Yeah.
But in this case, we're just talking about a solid without pores.
Okay.
When you add the fluid part, it gets a little bit more complicated.
Well, but then the data you showed, they are solid with pores, right? That's real
Yeah,
data.
yeah.
In here, we are creating a simplified model in front of the.
Yes, but the same thing will hold in terms of effective stresses. So here I'm comparing effective stresses to the effective stresses to cause this tensile strength failure. Yes, Stephanie.
Aren't rocks poor thermal conductors? So if you're increasing temperature through like a frac,
Yeah.
on what scale is that temperature difference actually penetrating the rock?
Okay, that's a very good question. And the answer is that usually the front of temperature, it's a lot shorter than the front of fluid invasion. It would depend on the permeability of your rock. But way ahead from the fracture, you're going to see changes of pressure because of the injection of the fluid. After that, you will see the injected fluid into the pores of the rock. And after that, you will see the front of change of temperature. So change of temperature, and that's one of the limitations we were saying with this cryogenic fracking, that do not go far from the point in which you start changing the temperature. And that's going to be related to the diffusivity parameter of the rock. And that's going to control how much temperature changes with time.
So
Jack, yeah.
So the stress and the difference in temperature created, can they travel far distance?
The what?
The stress that the changing pressure created, can they travel
Yeah.
in far distance?
Yeah, because say you contract the rock here, and that's going to create additional displacement for the rock further away to move a little bit closer. Okay, so now that we have the basics of thermoelasticity, we can apply this to my favorite example, which, do you think which one that is? We're going to apply it into more or less a real condition. What boundary conditions are the closest? Very simple, still very simple, but closer to actual conditions. Which one?
Oh, yeah,
The uniaxial strain, yeah. So 1D strain case. And for this uniaxial strain case, again, we have rock which is in the subsurface. There is more rock around it in both horizontal directions. Let's say that we're planning to make an injection over here out of the vertical wellbore. And we want to know how much stress is going to change as a function of temperature. Okay, so we'll start by writing the same equation that we wrote before. Constitutive equation. And I'm going to do a small change here so that I don't have to write this delta all the time. And I'm going to call theta to delta T equal to T minus the original temperature. All right, so let's start with this. We're going to write this equation in terms of effective stresses. And the same thing is going to apply for a porous solid in drain conditions as far as when I'm injecting this fluid. I forgot also my red pen. But I'm injecting this fluid, which is cold, and the formation is relatively permeable so that the changes in pressure are negligible. All right. So let's start with the equation. And let me add a coordinate system over here. So I'm going to make this, let's see, 1, 2, 3, 1, 2, and 3. So I have sigma 1, 1, sigma 2, 2, sigma 3, 3. Here I have stiffness matrix, and stiffness matrix is this one. Strains, and last we have the thermal components. All right, so let's start with the 1D condition. The one-dimensional condition means that I can have stresses in direction 3, but I'm not going to have any strain in direction 1 or 2. And I'm saying that I'm injecting, the same equation is going to hold for either hot or cold, right? But let's say that we inject a cold fluid, and therefore I would expect a contraction, and if I have a contraction, the deformed configuration of the rock after some time is going to be a contraction just in direction 3, but not in direction 1 and not in direction 2. So this one will be 0, this one will be 0, and let's see how we work with those equations. I'm going to assume something else over here, which is required. So because I assume that the overburden is constant and that there is also a very small change of pressure, which is negligible, those two together are going to imply that also sigma 3 is relatively constant. Okay? So this one is going to be constant. All right. Let's write equations for sigma 1 and sigma 2. So sigma 1 basically is this rho times that, and you know these are 0, so this is just going to be 1 minus Poisson ratio epsilon 3 plus 3 beta k theta, and sigma 2 is going to be the same, so I'm not going to write it. Sigma 3 is going to be, no, wait, this, the first one is wrong, because just Poisson ratio. I was somehow looking at the third row, but it's just Poisson ratio. And the third one is 1 minus Poisson ratio, modulus 1 plus 1 minus epsilon 3 plus 3 beta k. And from here, what I want to do is I want to use this equation into this other equation. So I get rid of the epsilon 3, and therefore this is going to be 1 plus this, 1 minus that. Epsilon 3 is going to be sigma 3 minus 3 beta k times that, and all of that divided this, and finally plus 3 beta k theta, and this is the fun part, you get to simplify things, and they naturally disappear, and as you can see, we have sigma 3 over here and the 3 beta. So let me see how we simplify this. So we know this coefficient very well, so it's that one, sigma 3 plus, I think I don't forget anything, we have the 3 beta k yeah, I think this is correct, right?
Why is this split?
I have a slightly different equation here in my notes, but I think this is correct. So common factor, right? 1 common factor. Oh, okay. I'm forgetting this. I knew that was the case. That's going to be like that. All right. So this is going to be the equation for the horizontal stress. In addition to the effective stress part caused by the effective vertical stress, now we have this other component due to changes of temperature. And what I'm interested in this particular case is what is going to be the variation of the effective horizontal stress due to a variation of temperature when I hold the effective vertical stress. And this is going to be basically the partial derivative of this, and it's going to be 3bk, and if I go ahead and do this operation, it's going to be 1 minus 2, 1 minus Poisson ratio, and I'm going to go one more thing. Hopefully my equation is going to be right. I'm not copying what I have here. I'm going another route. And what was K? You remember that? Okay, this.
Wait, isn't it 3bk minus everything in that parentheses?
3bk?
Don't you distribute it and then take the derivative?
Yeah. So.
Why it wouldn't be 3bk minus?
No, but I'm already doing this thing over here.
Okay.
So K is Young modulus divided 3 times 1 minus 2 times the Poisson ratio, right? That's K, right? And this times 1 minus 2 Poisson ratio 1 minus Poisson ratio. And again, this is the fun part, goes away, and I get that this is just beta Young modulus 1 minus Poisson ratio. So if I increase the temperature, this is positive, this is positive, this is going to be positive, I'm going to get a compressive stress. If I decrease the temperature, the change of effective stress is going to be negative. So I'm going to have more tension. And with this we finish. For the typical numbers that we were using before, beta 10 to the minus 5, 1 over k. Let's say Young modulus 10 gigapascals and Poisson ratio of 0.2. What this equation tells me is that the gradient of the change of stress caused by the change of temperature holding effective vertical stress constant is going to be 0.1 degree, 0.1 MPa per degree. So if you have a change of temperature of 10 degrees, then you get 1 megapascal. If you have a change of degree of temperature of 100 K, then you're going to get 10 megapascals. So this, as you can see, this is quite significant. And these stresses can change the stresses in the reservoir quite a bit. So let's come back over here. If you have lower stresses caused by temperature, again, you may be injecting a fluid. At the beginning, everything is fine, but then at some point when the rock starts to cool off, you may have a hydraulic fracture propagating. Because also change of temperature, you could, if your rock is shrinking, you could have also a reactivation of a fault. Because you're changing, well, let me actually draw this reactivation. It's going to be probably limited to inside the reservoir. Because you're shrinking the rock in the horizontal direction, you're lowering the effective stress, the normal effective stress on the fault. If your shear stress is more or less the same, you have the risk of fault reactivation. So because of the injection of this cold fluid, then we have seen that we can lower the fracture gradient, and we can, if that goes far away, we can even cause some induced seismicity. And this has been a big problem for geothermal energy. In the field experiment in Switzerland, nobody knows yet what happened really, but I guess some people know, but at least I don't know. What was the main cause for some induced seismicity they observed? So they were doing geothermal energy, pumping cold water, getting cold water out of the ground for producing electricity, but then they started to observe some induced seismicity and they stopped. Where does induced seismicity comes for because of injection and increase of pore pressure, or reactivating a fault, or by temperature reactivating faults. And nobody knows that very well. So that would be something that we don't want to do, like large induced seismicity because of injecting cold fluids. At the same time, this is beneficial for geothermal energy whenever you are reactivating some small fractures, because in that case you have an increased permeability near fractures that can help the cold fluids to get into the matrix of the rock to suck the heat and take it into another wellbore that is going to produce the hot water. Jack, you had a question?
So when we talk about induced density, a lot of the induced density occurs near the basement, so it's lower than the injection point.
Yeah.
And then in here we only talk about the change in pressure with respect to sigma 1,1, so that's horizontal. What about vertical?
Okay, well, in this case, we're assuming that, again, the change of pressure are very small
With respect to vertical or
everywhere. Everywhere. So there are two parts in this problem of injection. How much you change the pore pressure, how much you change the temperature. But for this particular problem, we're assuming that the part of changing pressure is not that important. And if we do that, we can derive all of these equations that, again, they don't have pressure in them, but they are still valid for effective stress, because I'm assuming that the changes of pressure are very small. I don't know if that answers your question, but I think you were asking me about what is the variation of sigma 3,3.
Yeah.
Well, in this case, since we're assuming that S33 is constant and it's just the overburden, temperature is not going to change the overburden. So that's going to stay the same. As long as we consider that this is a very long layer.
Yes.
If you consider more like a localized change of temperature, then you could create some arcing effects near that localized point. But we're not exploring that right now. We're assuming that we have a long reservoir with dimensions in horizontal direction much larger than in vertical direction.
So we make no limitations on the changes in S11 and S2, right? Because we have a trend in sigma 1,1, we would have a trend in S11 too.
Yes. So we don't have any strains in direction 1 and 2, but we let temperature change the deformation in direction 3 anywhere. So if there is a contraction, the rock is just going to contract in direction 3, but not in direction 1 and 2.
Yes. And are we considering fluid in this case or no?
Not directly,
Not directly.
but indirectly, what is changing the temperature is the fluid.
What changes in the temperature? Oh, yeah.
So we're not assuming here an impervious rock. There is permeability, fluid goes through,
Right.
and fluid changes temperature.
Yeah.
And as the result of that, that's why the change of temperature localizes in this layer. But we're saying the change of pressure is so small, let's say 0.1 MPa, that compared to the changes of stress that we see because of change of temperature, then we just disregard those. That we said that they could be as large as, for example, 10 megapascals.
Then how much in length would the temperature change in the solid?
100 C.
Okay.
Or at least, whatever number, you multiply that number times that, and that's what you get. So theta is the overall change of temperature. All right, okay, guys, it's 5:30, and we just have one more thing to do next time, but that's going to be it for today. And, again, same problem, 1D strain, but with another type of action, which in this case is temperature. Okay, well, see you on Wednesday.
Thank you.
Thank you.
Can you send me the